Hi, my name is Sun Young Kim, and today I will present our work on metric learning beyond class labels via hierarchical regularization called HIRE. In this presentation, I will first provide a concise overview of our work. HIRE aims to provide enhanced and detailed supervision beyond the interclass separability induced by common metric learning approaches. It achieves this by enabling the model to discover and utilize the latent semantic hierarchy through soft hierarchical clustering without the need for additional supervision. To accurately represent the semantic hierarchy, HIRE leverages hyperbolic space as the embedding space. Importantly, HIRE seamlessly integrates with conventional metric learning losses that are based on Euclidean distance or hyperbolic distance. I will start by discussing the motivation behind our proposed method. Deep metric learning aims to learn an embedding network so that semantically similar images are closely grouped together while other samples are separated apart. Traditionally, semantic similarity has been defined based on class equivalence. Consider the example of the Laysan albatross and the shiny cowbird, which belong to different classes. These have completely different semantics, making it natural for them to be far apart from each other. Let's consider another example. We have the Laysan albatross and the black-footed albatross, which belong to different classes, but share the same superclass. This indicates that they are not entirely distinct in terms of their semantics. This example clearly shows the limitation of the binary relation of equivalence. It fails to capture the real-world semantic similarity and only addresses a small subset of possible relationships between samples. It becomes evident that we need more comprehensive supervision, such as a semantic hierarchy, to fully grasp the nuanced semantic relationships within the data. In the realm of deep metric learning, the choice of embedding spaces is of utmost importance. Most of metric learning models commonly utilize spherical or Euclidean embeddings. However, Euclidean space cannot embed large and complex graphs like hierarchical tree without distortion or loss of information. In contrast, hyperbolic space of negative curvature possess geometric properties that make embeddings well suited for modeling hierarchical relationships. In hyperbolic geometry, there are various models to represent hyperbolic space. However, for our work, we focus on the widely known and extensively used Poincare-Ball model. The hyperbolic distance between two vectors in the Poincare-Ball model can be formulated as this. An interesting characteristic of the hyperbolic distance is that the lines connecting points in the figure all have the same hyperbolic distance. Leveraging this unique characteristic, we can effectively embed hierarchical relationships into this hyperbolic space. And then we introduce our proposed method, HIRE. HIRE aims to discover the latent semantic hierarchy of data with no additional annotation for the hierarchy. In HIRE, instead of considering a specific sample as an ancestor, we employ hierarchical proxies that act as virtual ancestors of data points. These hierarchical proxies allow us to hierarchically aggregate data points, capturing the underlying structure of the data. The key idea behind HIRE is to ensure that related samples share the same lowest common ancestor, while the remaining samples have different lowest common ancestors. To achieve our goals, we employ reciprocal nearest neighbors to construct triplets comprising relevant pairs and another sample. We calculate the probability of a hierarchical proxy serving as the lowest common ancestor using distances and introduce Gumbel noise. This enables us to sample lowest common ancestors for both the relevant pair and the entire triplet. Figure illustrates the behavior of HIRE in relation to triplets and their lowest common ancestors. HIRE clusters relevant samples together while unrelated samples branching out. It encourages the proximity of relevant samples to their shared proxy while promoting distance from the proxy associated with the irrelevant sample. This encourages the proxies to represent different levels of the semantic hierarchy. The final loss function is a combination of the metric learning loss and the higher loss. Various loss functions, based on cosine or Euclidean distances, can be used for the metric learning objective. In this work, we utilize the proxy anchor loss. If we use cosine distance-based loss, the metric learning loss controls the angles, while higher adjusts hyperbolic distances based on positions and norms. Our experimental results demonstrate the effectiveness of our proposed method. Using the ResNet 50 backbone, we outperform existing CNN-based methods on most of datasets. Furthermore, our method consistently outperforms state-of-the-art VIT-based models. We visualize the learned embedding vectors in a two-dimensional Poincare ball using UMAP with the hyperboloid distance metric. In figure, we can observe the tree-like hierarchical structure between data and hierarchical proxies in the embedding space learned by Hire. We investigate whether Hire actually captures meaningful semantic hierarchy. In left figure, we compare the affinity matrix between classes in the embedding space trained with Hire and the proxy anchor loss. Interestingly, Hire clearly distinguishes between classes sharing the same superclass and others. However, the proxy anchor loss, where different superclasses often have high similarity, and right figure shows the subclass characteristics in Hire. We visualize the nearest neighbor samples of hierarchical proxies located near the boundary of the Poincare ball. These proxies capture pose variations in bird images. These suggest that Hire effectively captures subclass relations, enabling the model to learn intra-class variation and shared features across different classes. In summary, our work introduces Hire, a method that uncovers the latent semantic hierarchy and seamlessly integrates with existing metric learning approaches, resulting in significant performance advancement. Thank you for your attention. For further exploration, please visit our project on GitHub.